Dear physics majors, or aspiring physics majors, this video is for you. I am a physics major. I have seen what it takes to be a physics major, and I will give you one piece of advice. Take math classes, a lot of them, and don't just do the minimum to get past your physics requirements. You need a lot of math to understand physics. Guess what? All of Einstein's general relativity, the theory of space-time and geometry that has brought me to tears, and one of the two subjects that I've actually cried due to its sheer beauty in describing the geometry of space-time and gravity as curvature of space-time. Who invented this theory? Was it Einstein? No. Guess what? All the technology behind this theory was invented by Riemann and Gauss in their understanding of curvatures. And the Riemann tensor is the integral piece of the Einstein field equations. The Einstein field equations are just using the technology of the Riemann curvature tensor. The Riemann curvature tensor, who invented that? A mathematician. Now, this just goes to tell you that, okay, obviously, this is way more nuanced of a topic, but take a lot of math. You need to know advanced math, not just the basic requirements for your physics degree. You need advanced math, at least the requirements of a math degree, in order to understand physics at a deeper level. And you'll run into roadblocks and you'll run into problems later on in your education. I have people in my quantum field theory class that are struggling, that are deeply struggling to understand quantum mechanics and quantum field theory, as well as general relativity. People in the general relativity class, why are they struggling? Because they don't know manifolds, they don't know PDEs at a high level, okay? They don't know analysis, they don't know real analysis, they don't know spectral theory, they don't know functional analysis, they don't know manifolds, and all of these things are the mathematical ingredients that go into physics. So if you want to understand physics at a deeper level, and you want to investigate the nature of reality, okay, you need math, and not just the math that they'll teach you in a physics major. And don't wait until it's too late and you're way too advanced in physics and you haven't taken enough math, and then you're kind of having to go back and relearn math from scratch. Take math courses from the very beginning. Take math seriously. Even math that might seem completely arbitrary, like algebra, okay, not the algebra that you learn in high school, the undergraduate pure algebra, which is one of the three pillars of math: algebra, topology, and analysis, okay? Algebra might seem so pure and abstracted, it might seem like it has nothing to do with physics. Guess what? It's integral to physics. In fact, it shows up at the core of physics. Why? Because algebra is the study of symmetry, and physical theories must respect the symmetries of nature, the underlying symmetries of nature. So guess what? Algebra plays a key role. Topology, it seems completely abstract, the study of shape and geometry. What does that have to do with physics? Well, guess what? Topology, differential topology, forms the basis for the study of curvature, which is how we understand space-time as a curved manifold. Okay? And then analysis, I'm not even going to mention analysis. Analysis is the most important in my personal opinion. That is my opinion, okay? My opinion is that analysis is the most important because it forms the building blocks of calculus of variations and classical mechanics, okay? Calculus of variations and classical mechanics. Why are those important? They are the foundation of all of physics. Every physical theory is built on the pillar of classical mechanics. Classical mechanics is essentially a generalization of Newton's second law, F equals ma. The F equals ma is a classical view of nature, and classical mechanics essentially says that this law, F equals ma, stems from a more deeper law, which is called the principle of least action. In Lagrangian mechanics. There's a great video you can watch, even if you don't know much physics, by Veritasium on Lagrangian mechanics, just to kind of get an idea. The idea is that it's the same thing as Newton's mechanics, F equals ma, but it's brought into a more cohesive mathematical package, a more powerful mathematical technology that can solve way more difficult problems, okay? And all of classical mechanics is built on this idea, this concept of calculus of variations. Calculus of variations is an analytical topic. It uses the branch of math called analysis. So study analysis, study calculus of variations for classical mechanics, okay? Then study algebra, okay? Algebra for notions of symmetry. Make sure that you study Lie algebras, Lie groups, and manifolds to understand general relativity, and make sure that you understand linear algebra and PDE and differential equations, because linear algebra shows up everywhere. It's just no questions asked. You're going to have to do numerical to do physics. You're going to need to know linear algebra to do physics, as well as almost any scientific discipline. And then, on the last note, PDE and ODE, of course, PDE, partial differential equations, those are the equations we use to model, every model of anything in the real world is a PDE, a partial differential equation, if it's a deterministic model, of course. If it's there are other models that are non-deterministic. The deterministic models are almost surely PDE, partial differential equations. And yeah, so I hope you take my advice up seriously and study math, even if you might think it's useless, even if it just seems super abstract. It is insanely useful, and you can just trust me that you're going to need it. You will need it, and you will struggle in physics if you do not focus on building your fundamentals in math and take math extremely seriously. All right, have a nice day.